Welcome to a chapter 12 general lesson video. So this video is going to encompass what was really covered in class, and there will be a separate video specifically on Grignard reagents and reactions that combine Grignard reactants with problems. Okay, but this will kind of have minimal Grignard problems. All right, we're just going to like touch lightly upon it, but I'm just going to do like a really quick rundown of kind of like the material that was covered. So we're going to start with lithium aluminum hydride and sodium borohydride. So what is lithium aluminum hydride? Well, lithium aluminum hydride kind of looks like this. Okay, so it's like a little plus sign right there. And then we have aluminum, right? So it's Al. Just put like a little A or L. And you have a hydride right here, or hydrogens, I should say. And what happens here is that basically, if you see LiAlH4, just ignore it and treat it as if it were equal to a negative hydrogen or a hydride, right? But how do we generate this? How do we make that? Well, what happens here is that aluminum is actually less electronegative than hydrogen. So when this bond breaks, the electrons are actually going to go towards the hydrogen, thus making an H negative. Okay, and the same thing can be said for sodium borohydride. So you can literally just replace lithium with sodium and aluminum with boron, and you would have the same compound, like the same idea. Okay, so let's get more into detail about what you can do with it and how you can apply it to some problems. So we're going to be comparing lithium aluminum hydride and sodium borohydride with what you can do with it, okay? And then we're going to go with the reaction, and you know how I like teaching. I like teaching the reaction within a problem, but we're going to make a tiny chart that you can copy. Okay, so lithium aluminum hydride, and we're going to have sodium borohydride, and we will have some aldehydes, if I can spell it correctly, aldehydes, some ketones, we call it ketones, and some esters. Okay, so what can you do with it? Well, lithium aluminum hydride is like the big boy. Okay, so that's a big boy, and he's really strong. He's like super strong, but since he's so strong, he's very reactive. Okay, imagine kind of like Arnold Schwarzenegger, right? He was very strong, but if you got him mad, he would actually hurt you, which is true in real life. You can use him to do a lot of things, but he's very reactive and he's not that friendly to work with, okay? So aldehydes, he can do that. Ketones, he can do that. And esters, he can do that, okay? So sodium borohydride actually works with aldehydes and ketones, but he fails for esters. Why? Well, because he's weak. He's very mellow and weak, and as a result, he only works on aldehydes and ketones. But Brian, what do you mean by aldehydes and ketones? What do you mean by they work like that? Well, these guys, they can convert aldehydes, ketones, etc. into alcohols. So they can make alcohols. Okay, cool. Now that you have the chart, we're going to do question 1, and I'm going to show you the mechanism, right? And afterwards, I kind of want you to work out questions 2 and 3. So let's see if you know how to do this. Now, we're assuming that you have excess amount of these materials, okay? So for question 1, you don't have one lithium aluminum hydride. You have enough lithium aluminum hydride to do this to completion. Okay, so let's draw our structure right here. Then we have an OCH3. And of course we have 2 carbonyls, which are pretty cool. I always think they're like little people or something. But notice that this guy right here is an ester, okay? And we're treating this with lithium aluminum hydride. So we're going to look at our chart, and eventually you'll do it so much that you have these memorized, right? Okay, well, what do I have here? I actually have a ketone. So I have a ketone, and I have an ester. So notice that if I use lithium aluminum hydride, I can get rid of the ketone and I can get rid of the ester. So that's what I'm going to do. Here's a reaction. Of course, we have lithium right here, and we have some hydrogens attached to this, aluminum. Almost said aldehyde. By the way, I hope you're having a great day. I sure am. Okay. Aluminum is actually less electronegative than hydrogen, so when the bond breaks, it forms a hydride. Okay. Right. So what happens now? Well, let's start with the ketone because it's a bit simpler to do the mechanism. Right here, what happens is that this bond breaks and goes towards the oxygen. That happens because between the carbon and the oxygen is a lot more electronegative, and hence is going to be attracting the electrons. Okay, so therefore we would actually have the substrate like this. That's a 3. That's a bad 3 right here, and we have some negativity right here. Okay, so that was negative, so that must mean that this carbon is positive. And of course, the hydrogen is going to be attracted to the positive side. So he's going to go over here. Okay? And now you have this guy. Now this takes a long time, so after this problem, we're just going to go into it, okay? Because you can just replay this section and replay the mechanism. So now you have O negative. And this O negative came from an alkane, right? Or from an alkene. So whenever you have like an R chain, like a random carbon chain, and then an O negative, that's actually called an alkoxide. And you should know that tertiary alkoxides they're better than secondary alkoxides, and they're better than primary alkoxides. Okay, so that's a 1, right? And this is a greater than symbol. Okay, so that must mean that alkoxides that are tertiary are more stable and more favorable than secondary alkoxides. Okay, so that's pretty cool. Now that's done, and then we're still in step 1. We're still in this section right here. Okay, we're not doing step 2 yet. Step 2 now is to do it on the ester, and the ester is just a carbon with 2 oxygens attached to it. Okay, one of them being a carbonyl. So what happens here is that another H from a different aluminum hydride, from a different one, comes in and it takes out this double bond, and we insert an H or hydride right here, and we have this. And of course we have our added hydrogens right there. Okay. But now what happens here is that something tricky happens. These electrons can go back in to the carbon. They go zoop, and they make a double bond. And what's the problem with this one? Well, let's cut this. Let's pretend that the left-hand side doesn't exist. Okay, let's call that an R. Well, what happens here is that now you have this guy. For a split moment, this center carbon, has 5 bonds. 1 to the other carbon chain, 1 to the hydrogen, 1 to the oxygen, and 2 to the oxygen. Okay? So that's 5 bonds. And that's not really good, is it? Now, what am I going to cut off? Am I going to cut off the R bond? Am I going to cut off the hydrogen bond, or am I going to cut off the oxygen? Well, no, Brian, you're actually going to cut off this bond, okay? So he comes out completely. Right? And let's erase some things because it's getting real messy. That's super good for me. Okay. So now what happens here is that we have this, an alkoxide, a double bond right here, And of course you have your hydrogens. But then you also have this broken guy right here, okay? Which is O negative CH3, right? Okay, well, technically you're done. Technically you are done, right? But like, what do you do? Well, remember how this bond broke? Well, those electrons left the carbon, so that must mean that this section right here is going to have a partial positive, okay? Because the electrons left right here. So that means that another lithium aluminum hydride can actually donate it's a mess, can donate another hydrogen. And this breaks right here. So therefore, you would have this. So that with like 2 added hydrogens. Okay, and then of course OCH3 negative. And now we're done. Okay, we're done. For step 2, you add the acid, which is hydronium. And all that happens here is that your alkoxides, or your O negatives, get rid of the negative signs and add hydrogens. Okay. But what does that mean? It means that instead of having this mess over here, we're going to be adding some hydrogens. So after step 2, we do an acid workup, which is when you add acid and you create your alcohols. So notice that we formed a secondary alcohol and a primary alcohol. We also formed methanol in that reaction. Okay, so to make a long story short, what happened here in this reaction is that basically a hydrogen or a hydride came in right here. This broke off to the oxygen, it became negative, and then another one came in right here. This bond broke to the oxygen, and then it came back right here, broke off this oxygen bond, and then broke again. So it's so ridiculous, you know? It broke off again towards the oxygen, and then that was it. So we added 2 hydrides on the ester, okay? 2 hydrides on the ester. In total, you would need 3 hydrides to do this. And then your acid workup would actually take all those negative oxygens and make them positive. Food for thought. Pretty cool. So let's do it again for step 2, for question 2. So in total, if you're basically running out of time, you see this, you're like, okay, well, this is a ketone, that's an ester, we have a lithium aluminum hydride, and then an acid workup. So my answer should just be like this. And then plus some OCH3, okay? Cool. Now for question 2, we're working with sodium borohydride. Now sodium borohydride works for aldehydes and ketones, but not esters, okay? Not esters. Cool. So over here we have an ester group. Is my sodium borohydride gonna mess with it? No. So my answer should still have an ester group, but it should also have an alcohol. It should have an alcohol because I see a ketone. Now this is a lot more simpler because we're not working with esters right now. We're working with ketones. So it's just one simple addition of a hydrogen, or of a hydride. So here we go. We have OCH3, that's going to stay the same right here. And then we're adding sodium borohydride. Okay. The hydrogen breaks off, becomes H negative. And then this bond is going to break out towards the oxygen, making this carbon positive. The hydride is going to be attracted towards the positive carbon, and it's going to form this. So we formed an oxide right here, and we added a hydrogen, right? And then that's it. That's step 1. Step 2, we add water, which is going to act as an acid. So the water comes in, right? This breaks off, this is a positive hydrogen, so it's a proton. He sees this negative oxygen, and the oxygen is going to pick him up. And thus we form an alcohol. This is secondary alcohol, which is pretty good. So this right here would be a secondary alkoxide. Okay. So that was the reaction. From now on, we will be referring lithium aluminum hydride and sodium borohydride as just H negative. Okay, so I don't want you to think of this. I want you to think of H negative. Okay, makes it more easier to draw and saves time. Okay, so now we have a cyclic compound, which is terrible. Who told me to draw? Terrible. Right. So of course this is an ester, and we're using lithium aluminum hydride. The H, or the hydride, comes in. He breaks over here, comes into the positive carbon right here. We form the alkoxide, which is secondary, and a hydrogen. Okay. But now, again, these electrons right here can actually kind of like laugh at us and come back into the bond area, forming a double bond. And of course, you see the type of problem that we're dealing with when that happens is that we have too many bonds on carbon. Carbon has 5 bonds. Well, that's really bad. Now you should know that this bond actually breaks towards the oxygen, the bottom oxygen, breaking the ether. Okay, so we're kind of like opening a ring. So we're doing like a ring expansion. And we're also making alcohols from this. Okay, so now this happens. And we have like this O negative. But then since this oxygen got some electrons, it got them from this carbon. So that must mean that this carbon is partially positive. Partially positive. So now another hydride comes in, attacks us, breaks this bond right there, and makes this. So now we added 2 hydrogens, okay, and an alkoxide. And then you can do acid workup and just take out your alkoxides, okay? So now you can have an alcohol right here. Like that. That's your answer, okay? So I'm just showing you the reactions, and you should be fine by now. So for question 4, what reactant would actually give us this product? And we can use lithium hydride, we can also use sodium borohydride, but what is going to give us this product? Well, since we can use both acids, or I guess hydrides, well, I would say that it can either be a ketone or it could be an aldehyde. So you can pick whichever you want, okay? So you could have picked pH, double bond oxygen, that's fine. Or you could have picked pH, let's do a ketone, right? It's perfectly fine. It's fine. Actually, I guess over here you would pick an aldehyde, right? Because then that could just come out and become an acid, right? Alright. Over here, you can only use lithium hydride, but not sodium borohydride to make this one. Well, then we're forced to make an ester. Why? Well, lithium aluminum hydride, it outdoes sodium borohydride in the fact that it can do esters, okay? So it can do everything that sodium borohydride can, but it can also do esters. So we can do pH, and let's do an ester group. There we go. Pretty cool. Now we draw the mechanism for the following reaction. Very fun. Cool. Over here we have pH. Then we have kind of like an aldehyde. Not a positive, it's actually a negative. Okay. These bonds break. He becomes partially positive. He's going to attack the carbon. Thus we will have pH like that, and then the added hydrogen right there. Okay, and then we're going to do kind of like an acid workup, because this is just methyl hydroxide, which kind of, it acts like a weak acid kind of. So now all that you need to do is just add an acid. Oxygen is going to be attracted to the hydrogen, the proton, thus giving us a primary alcohol. There we go. See, pretty simple, pretty fun. It gets a little complicated when you get into esters, but it's not that bad. Okay. Speaking of esters, gosh. Okay. Terrific. Now we have, I'm not going to redraw this, my gosh. We have H negative. This breaks down. He's going to be attracted to this carbon right there. Of course, you can do it with me, I guess. But yeah, today was alright. Hope it gets better. They have a hydrogen. Yada yada, whatever. These electrons can then pop back in there. Carbon has 5 bonds, doesn't like that. It's going to release some oxygen, or it's going to release some electrons towards the oxygen, thus making this carbon technically positive. So now we have O. This is double bonded. Right there. Now another hydride comes in, and it's attracted right there, thus breaking this bond right there. Okay, so now we have O right there. Of course, arrow pushing is really helpful. So now we have our 2 hydrogens. Okay, and then you do an acid workup, and then technically you can remove the alkoxides and just replace them with alcohols. Pretty fun. Hope that helped. We're going to be moving on to the next subject. Love you guys. Now we're actually going to be forming alkoxides, which are those little R groups with that O negative. So R in this case is like random carbon chains, like carbon, hydrogen, carbon, 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 etc. And then at the end of that carbon chain is an oxygen that is negative. But how do we make an alkoxide? Because alkoxides are actually going to be favorable to make alcohols if you do an acid workup. Okay, or you can make ethers, etc. with a nucleophilic addition. How do you do that? Well, in this case, you can use it. You can make alkoxides via sodium or like metals, right? So, for instance, this sodium is going to be partially positive, and so what happens here is that this pH, it's a very bad P. This phenyl, right? This phenyl is going to go over here. And if you figure out what a phenyl is, it's kind of like a benzene ring that's directly attached to the carbon. Okay. This bond breaks, making this oxygen negative. And then you have sodium hydride. Okay. So positive and then negative. Woo! And that's it. That was step 1. Pretty cool, right? Alright, over here, now you're treating it with step 2. Step 2, what happens here is that the bromine pops off, making a positive carbon. And this positive carbon is actually attracted to the alkoxide, right? So he comes here. Yeah, alkoxide. I'm saying it right. Thank you. So now we have pH and right here. And look at that. We actually made, let's see, 1, 2, 3. We actually made an ether. You saw that? That was pretty cool. And so that's pretty favorable to do. Why is that? Well, it's favorable to do because it goes via an SN2 route or reaction. Okay, it's an SN2 reaction. That means that there are no carbocations. Okay, that means no rearrangement. Right? And another thing they should know is that your reactant right here, this guy, preferably you want him to be a primary. Sometimes a secondary is okay, but primary is going to be really good because of SN2 reaction, okay? So while the process of removing the hydrogen is not an SN2 process, the addition of the carbons is an SN2 process, okay? So step 2 is SN2, right? Okay, so, you know, you want your, let's say, R group, your kind of like RX, you want to be primary. And you want it to be like a good leaving group, right? You don't want to have like a R group with an alcohol, right? Because alcohols are pretty bad leaving groups. If it was a water, it would be pretty good, or an iodine. So that's kind of like the main gist of what we're doing, okay? And you're going to see in the next problem that you're going to have kind of like a weird thing that happens to the stereochemistry. Okay, so let's jump right into that one. Okay, so what happens here? Well, what happens here is that, again, the bond breaks between the O and the H, and the sodium is gonna, basically the sodium is gonna pair up with the hydrogen, okay? So he's gone. But now look at this. Look what's weird. We now have an alkoxide that is chiral. Well, what do we do? Well, now we're adding this guy, right? So he's going to break towards the bromine, thus forming a negative carbon, right? Or a positive carbon. And he's going to be attracted to this oxygen. So we will have this. Now, be very, very careful, okay? I made this mistake a couple of times when I was studying this, but you're not going to do that. This does not invert. Why does it not invert? I thought that whenever we have an SN2 reaction on a chiral carbon, we do stereoinversion, meaning that the wedge becomes a hash, or the hash becomes a wedge. Well, that is true, but notice where I did my addition. I did my addition directly on the oxygen. I didn't do it on the chiral carbon, okay? Just because I put an addition on the oxygen doesn't mean I can do inversion. That only happens if I added it directly onto the carbon, right? So if I added my carbon into this carbon, then yeah, that would be an inversion. But notice that I added it directly onto the oxygen, okay? So first of all, step 1, that keeps stereo. And then step 2, well, that could do an inversion. So could invert if it added directly onto the carbon. In this case, it added onto the oxygen, therefore there is no inversion. Okay, for the last question, over here we're doing kind of like a hydroboration, anti-Markovnikov reaction, and you can tell that it's going to be anti-Markovnikov because you have a peroxide right there. Now I'm not going to get into the mechanism for that one, simply because it's radical reaction and because there's a video on it, so you know I'm not going to waste my time. So of course, to recap, what would happen here is that this carbon technically has a hydrogen, and this carbon also has 2 hydrogens. So now we have to pick which area we're going to go to. Well, anti-Markovnikov says I want to add my alcohol, or I should say, I want to add my hydrogen to the area where it would have the least amount of friends. So it would be in this area. Therefore, we're going to add our alcohol on that area. So after you do that reaction, you're going to have an alcohol like this. Okay, now in step 3, you're going to take out that hydrogen and make an alkoxide. After that, you're going to be adding this guy via SN2 reaction. Okay, so ignore the bromine, and we're just going to add 2 carbons. So let's do that. 1, 2. And look at that. Hey, dude, you made an ester. So, actually not an ester. I'm sorry, an ether. So I'm very proud of you for making an ether, and I hope that you continue to make ethers in your life. Thank you. Let's move on. I personally love PCC and hydrochromic acid. It makes me feel real smart whenever I make like a correct answer. And you're going to feel really smart after this section. So let's get into it. Right here, I can't add anything because my program's weird. But now we can. Okay. So, right here, PCC is also called pyridium chlorochromate, I believe. But the only thing that's really important for you to know, I'm not drawing it out, by the way, forget that, is that it makes a primary alcohol into an aldehyde. Okay, so primary alcohol into an aldehyde. So what should we expect for question 1? Well, after treating a primary alcohol with PCC, you're going to be expecting an aldehyde. So pH, that. Okay, so that was it. Simple. Now, what about hydrochromic acid? Well, hydrochromic acid, technically this is, jumping back, PCC is more of like a weak, like a mild reactant, but hydrochromic acid is super strong, okay? Super strong. And it gets a little bit more complicated, but basically it can do secondary and primary alcohols. So for primary alcohols, instead of making an aldehyde, it makes a carboxylic acid. And if you forgot what a carboxylic acid is, it's basically R, carbon, double bond with that, and then OH. Okay, just like that. Yeah, so that's what it makes. But what about a secondary alcohol? Well, secondary alcohol, it's kind of like its main use, I should say. Well, it makes that into a ketone. Okay, so that's what you should be expecting. But if you have a tertiary alcohol, then there's no reaction. Okay, so we're gonna put very frowny face right there. All right, so that was it. Oh, before I forget, if you have an aldehyde, it'll make that into a carboxylic acid. All right, so that was it. Aldehyde into carboxylic acid, primary into carboxylic acid, secondary into a ketone. Not too much to remember, you'll be fine, okay? So let's jump into these practice problems and we'll just knock them out. Okay, so by this time you would have paused the video and you would have copied that little chart into your notebook or tattoo it somewhere, probably your forehead. That'd be fun. Right here we're working with a primary alcohol. So what do you know about primary alcohols when you're treating with hydrochromic acid? I'm not showing the mechanism, I don't think it's worth it. So we're just putting in the answer. We're gonna put pH, which is a phenyl. It's like a benzene ring directly attached to this carbon, okay? And you should be expecting a what? That's right, a carboxylic acid. Okay, so let's do that. So it's like this. Simple. Okay, now you're doing a secondary. And what's secondary for hydrochromic acid? Well, you're gonna get a ketone, okay? Like that. And now you're working with PCC. Well, over here, PCC, this is a secondary alcohol, and this is gonna be a primary alcohol. So what do we do? Well, for this case, you're gonna ignore the secondary because you can't do anything with secondary alcohol with PCC. Instead, you're gonna be focusing on the primary. And what do you get from a primary PCC? You get an aldehyde, okay? So we should still have a secondary alcohol, but instead, we're going to have an aldehyde, I should say. So here we go. So we have an aldehyde, and we'll just add an H, right? So that's our answer. And what about hydrochromic acid? Well, hydrochromic acid, it takes out the secondary alcohol and it takes out the primary alcohol. For the secondary alcohol, you're going to be expecting a ketone, and for the primary alcohol, you're going to be expecting a carboxylic acid. Pretty fun. Okay. So over here, we're going to have a ketone. And over here, we will have a carboxylic acid. Okay, and that's it. That's PCC and hydrochromic acid. Hope that helped. 5 minutes. Cool. Great. So now you know how to work with PCC and hydrochromic acid. But what happens if we start throwing in more reactions? Right? What if it's a multi-step reaction? Well, let's check it out. Over here, you have a primary alcohol with PCC. So what should you be expecting? You should be expecting an aldehyde. We have 1, 2, 3, 4, and then an aldehyde right here. And then in reaction 2, we're going to be treating it with MgBr, which turns out to be a Grignard reagent. We're going to touch on Grignard in just a little bit, right? Not too much, because there's going to be a separate video just covering Grignard with a lot of practice problems, and you'll be a master at it. But all you need to know is that pH, which is a phenyl, is directly attached to this MgBr, right? Okay, so MgBr, and it has to be MgBr. See, this would be wrong. BrMg, that's wrong, okay? It has to be MgBr in that order for the reaction to take place. So all that happens is that this breaks towards Mg, and we have a pH negative, okay? This bond breaks towards the oxygen, making this carbon a little bit positive, okay? It actually forms a positive carbocation, right? So now we have this. We have 1, 2, 3, 4, O negative, and then since this carbon is positive, the phenyl is going to go towards the carbon, like that, and then we have a phenyl pH. So that was done. After that, we're going to do an acid workup, meaning that my alkoxide, the O negative, is going to be treated with an acid, and we just make that alkoxide into an alcohol. So we create an alcohol, 1, 2, 3, 4. We have a pH right there, and then an alcohol. So over here, you just made a secondary alcohol, which is pretty good. So notice that, well, how should I say? Technically, you made a primary alcohol into a secondary alcohol. So overall, is this reaction favorable? You know, I would say that it is favorable because you made a secondary, which is more stable, from an unstable alcohol. So overall, that reaction is really good. So moving on to question 2, let's see if you can handle that by yourself. And when I'm done erasing this, we can actually jump into it. So now let's jump into it. Okay. We have hydrochromic acid on a secondary alcohol. So what should I be expecting? I should be expecting a ketone. Okay. So right here we have a ketone right there. And then we're treating it with an organic metallic acid, well, not an acid, but organic metallic compound, or just a Grignard reagent. Okay. Organic metallic compound is just a carbon chain with a metal directly attached to it. So if it makes you feel better, you can just ignore the MgBr and the little bond associated with it. So overall, we're just going to be adding 3 carbons, 1, 2, and 3. Okay. So we're going to be adding 3 carbons to this area. So this bond breaks, making this negative and this positive. And then the 3 carbon compound, 1, 2, 3, which is negative, is going to be attracted to this positive sign. And therefore, we will have this guy right here. And then 1, 2, 3, right? And then we just do a simple acid workup, which creates something like this. 1, 2, 3, and then just do an acid right there, an alcohol. So that was it. That's basically the problem. Okay, so they're very simple, very straightforward to work with. Okay, you just need to know what to do when you have a Grignard reagent. And again, a Grignard reagent is just typically MgBr or lithium. So it'll be like R MgBr, or it could be like R lithium. It's the same idea, same concept. Okay, so for instance, if I had let's say 1, 2, 3, 4, and then a lithium, well, I could just ignore this bond and find out that I'm working with 4 carbons. So 1, 2, 3, 4. And so overall, I'm just doing 1, 2, 3, 4 negative. That's all I'm doing, okay? So if you see any R group with a lithium, just treat it like a magnesium bromine, okay? Nothing bad. So now you're actually treating an aldehyde with a Grignard reagent. So what can happen here? Well, you can actually break this aldehyde. So again, we ignore the MgBr, and we're just adding a phenyl with 2 carbons. Again, the double bond breaks, right? And he becomes negative, and this carbon becomes positive. Okay. So that means that we have carbon like this. Positive carbon. So then that positive carbon is going to be taken over by the 2 carbon chain. So let's see, 1, 2, and then pH. Of course, you still have your hydrogen right there, which is fine. Okay. So now we're going to do an acid workup. So this alkoxide gets removed and is replaced with an alcohol. So the H just connected with the O negative. Now, after that, we're treating this alcohol with hydrochromic acid. So let's see what we should be expecting. Let's see. Our alcohol is attached to this carbon, and that carbon is attached to 1, 2. So therefore, it's a secondary alcohol. And what do you know about secondary alcohols with hydrochromic acid? Well, secondary alcohols treated with hydrochromic acid create a what? Ketone. So therefore, I should be having a 1, 2, 3, and then let's just do like a ketone. So let's do 1, 2, 3, and then a ketone. Yeah, I think that's right. So there you go. So carbon, carbon. Let's do a carbon right there, and we should be fine. So yeah, that should be your answer, and that's all you should be getting. Hopefully that clears up Grignard just a little bit, and PCC with multiple reactions, and HCr or hydrochromic acid within multiple reactions with acid workups. Okay, now we're working with PBr3, which just replaces an alcohol with a bromine, and it changes the stereochemistry. So this goes by an SN2 reaction. So SN2 reaction, it can also do an E2 reaction. Okay, and it's not good. So not good for tertiary alcohols. And we'll discover what is good for tertiary alcohols. In this case, here's a reaction. OH, and then we have bromine, actually phosphorus, like 3 bromines. Okay, so what happens here? Well, what happens here is that one of the bromines break off and the electrons goes towards the bromine, thus creating a Br negative. And then this is kind of positive. Okay, since that's positive, the oxygen is going to be attracted to the positive phosphorus. Okay, to the positive phosphorus. Therefore, you're going to be expecting something like this. And of course, you have your P, then your Br, like this. But now that oxygen has 3 bonds, 1 to the carbon, 1 to the hydrogen, and 1 to the phosphorus. Therefore, it's going to be positively charged. And that means that it can break off, right? So now we have a kind of like positive carbocation, not really. But anyways, it's slightly positive, and that must mean that the bromine comes in and replaces it. Now, of course, you're going to have a stereo inversion. So notice that we had a wedge alcohol. Now we will have a hash bromine. So now we will have a hash bromine. And there you go. That was your mechanism. Whoop-de-doo. Now for like the speed run, okay, well, we have PBr3. We have a primary alcohol, so we can totally do it. All that happens is that this breaks off and you replace it with a bromine. Cool. Secondary alcohol, it can totally happen. You get rid of this alcohol and then you add a wedge, kind of like the opposite of what you had, a wedge bromine. Simple. So now you're working with SOCl. I don't know the name, but I call it Socal. Right, so now we're working with Socal. And with this one is that depending on the substrate, you'll have different reactions. So for instance, if you're a primary, you're going to involve an SN2 reaction. And if you're a secondary, you're actually going to involve an SN1 reaction. Now, here's the mechanism for it, okay? So the mechanism for this, let's do it right here. It's that you have, if I remember correctly, it's like SO, and then we have a chlorine, another chlorine. And what happens here is that this bond breaks towards the oxygen, releasing this chlorine, okay? Well, eventually it's going to release, but you'll see. So this oxygen is technically more negative, and then he's going to be positive. That must mean that this oxygen is going to be attracted to the sulfur. Therefore, we have, go downwards, have that, still that, and then we have sulfur, and then single bonded oxygen, a chlorine, and a chlorine. Pretty cool. So what happens now? Well, what happens now is that the bond can resurface, right? Kicking out this chlorine. So we have like this, right? And what else? Sulfur. We have one chlorine now and a double bonded oxygen, okay? And this chlorine is just like hanging out right here. Okay, well now, since this is what? Originally this was a primary alcohol, so since it's a primary alcohol, it's going to do an SN2 reaction. Okay, well that's pretty cool. This oxygen has a triple bond, right? So there's 3 bonds connected to this oxygen, therefore it's going to be positive, and he's going to break off. Let's do it over here. So now we have this, okay, and this is going to be negative, actually, right? So actually it's going to be positive, so I'm sorry. It's going to be positive because the oxygen was negative, and this chlorine is going to be able to attach, thus giving us this answer, right? So that was it. I mean, that was the mechanism for an SN2 reaction, right? So not too much to understand or to comprehend, but basically, if you don't want to do the mechanism, but you know, it could be on the exam. If you don't want to do the mechanism, you could just do like this. Okay, well, it's a primary, blah, 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 who cares? Cl. Okay. Over here, one of the important things is that there is a stereo retention. There's a stereo retention, okay? So you should know that it also has a stereo retention. And all that means is that if you have a wedge alcohol, you're going to have a wedge chlorine. So this is what you'll have. So you're going to have a wedge chlorine. And that was it. So pretty simple. You know the mechanism once, you could just kind of like bamboozle your way into it. It'll be fine. Anyways, hope that helps, and I hope you do well on that portion of the exam. Do you remember when I first mentioned PBr3? And I said that PBr3 is for primary or secondary alcohols? Well, what happens if we're working with tertiary alcohols? Well, if you're working with tertiary alcohols, then most likely, for tertiary alcohols, you'll be working with a hydrogen halide, right? So a hydrogen attached to some halogen, which is bromine, chlorine, iodine, sometimes fluorine. Not really fluorine, but it's as an example. So what happens here is that you're going to be doing kind of like an SN1 reaction, right? So we have an H and then a Br. The Br comes off. You have an H positive, whatever. He's going to be attracted to this oxygen. We now have this guy, which is water. So he's positive. He's going to come off, forming a carbocation. Notice that this is a tertiary carbocation, which is really favorable. It's always going to make a tertiary carbocation because it's a tertiary alcohol. This is what you're doing it for. And then this bromine is going to come in and attack. Okay, there you go. Bada bing, bada boom. We have a tertiary bromide. Pretty cool. So that was the reaction. Now that you know the reaction, there's no reason for me to do it. Technically, you now have a water that leaves from the tertiary carbocation. And then this iodine comes in, it's negative, attacks, whatever, right? And then iodine. Pretty fun. Okay. And then this one comes off, it's a water, because water is a great leaving group. Oh, okay, so you want to do something, well, you would just add HBr. Right, I mean, nothing much to it, right? The hydrogen attaches to the alcohol comes out as water, the bromine attacks the positive carbocation, pushes itself in, there you go. It goes via SN1 reaction. SN1. So now we're going to be working with toluene, right? Or OTS, or I call them TOTS because it's what we form. Basically, I'm not showing you the mechanism. It's a mess. Frankly, I don't think it's worth it. All you need to know is that whenever you have TS, you're going to ignore the chlorine, actually. You're going to ignore the chlorine. And we're going to add this. We're going to have 1, 2, 3, 4, 5. We have this right here. We have OTS. OTS, right? The kind of like triethylamine is just kind of like a stabilizer for the toluene. Okay, so it just stabilizes it. Don't worry about it. Now, for number 2, we're actually going to be treating it with sodium methyl oxide, right? And is this going to be a SN1, SN2, E1, E2 reaction? Because toluene and mesylate, they can actually do any type of reaction, right? They're like super leaving groups, really good. Well, you should be saying that this is actually SN2 reaction. Why? Well, I know it's not SN1 and I know it's not E1 simply because it has a sodium. So if something has a metal, it's going to be really strong and it's going to be an SN2, E2 world. Now, this is a secondary alcohol, okay? Or a secondary OTS. So we're not adding any heat as well. That means that this is going to be SN2 reaction. And what do you know about SN2 reactions? SN2 reactions actually do stereoinversion for a chiral carbon. So this is what you need to do. We have 1, 2, 3, 4, 5, and then a stereoinversion, right? So let's see what we do here. We would still have an oxygen and then a methyl group. So the oxygen and methyl group came from this guy. That's all we did. That's all we added. There you go. Now you're treating number 2 with sodium. So we're going to rip this out, make an alkoxide, and then we're actually going to do kind of like a SN1 reaction, right? So what happens here, I mean, it's kind of like an SN1 reaction, but it's kind of not. It's weird. What happens here is that this bromine has this methyl group. And of course, it breaks off to make a positive carbon. And that positive carbon is going to be directly attached to this alkoxide. Okay, and we're still going to have some stereo retention. So we're going to have 1, 2, 3, 4, 5. But why is that? Well, technically it is an SN1 reaction because it's weak. But this happens because we added something directly onto the oxygen. We did not add it directly onto the carbon that was supporting the oxygen. Okay, so if I were to add this on the carbon, then yes, there would be a stereoinversion. But notice that I added it directly onto the oxygen, making it retain its stereochemistry. Pretty good, pretty cool. Also, did you learn something? Did you pick up on something? Well, yeah, Brian, I found out that if I want to have stereoinversion, most likely I'm going to have a tosylate and then kind of like a base. Right, so like a sodium hydroxide, or like sodium methoxide, then I would have a inversion. But if I want to retain something, I would just have a sodium and then add something, right? So this is kind of like retention, and this is going to be inversion. Pretty cool. All right. Now over here, of course, we're going to get rid of the hydrogen and we're going to put in the TS. So we're going to have some OTS right there. And now we're treating it with sodium ethyl, or not ethyl, but sodium triethylamine. I don't know why I was saying sodium. It's a long day. Really, really tough day. Triethylamine. So triethylamine is big and bulky. It's just a nitrogen with like 3 ethyls. 1, 2, then 1, 2, and 1, 2. So that's it. And what do you know about triethylamine? Well, it's big and bulky. And big and bulky is going to be E2 or E1. Do you see a metal? No. So it's going to be E1. Okay. Is it going to be Hoffman or Zaitsev favored? It's going to be Hoffman since it's really big and bulky. Hoffman means that we're going to be forming a unstable alkene or double bond. And it could be over here, actually. So that's what we're forming. So it's a terminal alkene. So therefore, you should be having something like this. Right, so it honestly wasn't that bad. And actually, my mistake, it's actually E2. So it's for reference, this is an E2 reaction. My mistake. Over here, we get rid of the TS, or the chlorine, we get rid of the hydrogen. We have 1, 2, 3, 4, 5. Then we have OTS. And after that, we cut that and add a methoxide, okay? But this is a tertiary. This is a tertiary right there, and you know, can we do SN2 E2? Well, I can't do an SN2 because it's a tertiary, and tertiary fails for SN2. The only option that I have is an E2. Now, is it going to be Zaitsev or Hoffman favored? Well, methoxide is really small. You know, it's not a tert-butyl, it's not a triethylamine. So it's going to be Zaitsev favored. That means I'm going to add the double bond right there on the middle. So we have 1, 2, 3, 4, like that. And then we have a double bond right there. See, not too bad. If you do more practice problems, you'll be fine. You'll be amazing. And that concludes our lesson on chapter 12 and some other things that you need to know. Of course, we're going to continue on another video, probably do epoxide openings and epoxide slicing, maybe some ether formation or Grignard. I'm not sure yet, but I hope that this video helped you and that you continue to study Ochem and have an amazing day. I'm glad that you watch these videos and they make me really happy when you enjoy them. So thank you so much for tuning in and actually listening to me ramble and mess up on some practice problems. So, of course, I hope you have a great day and that you know that you're loved. I love you. Have a great day. Bye.